Let's say we have the following periodic complex signal. This signal that simply goes around in a circle with a fixed frequency is called a complex sinusoid. The Fourier Transform tells us that any complex signal can be decomposed into a sum of these sinusoids, where the sinusoids have varying frequencies, amplitudes, and rotations. Next, I'll show what this decomposition looks like in an animated form. Here are the 6 signals that we will decompose into sinusoids. Notice the complex square wave in particular, which simply jumps between the 4 corners of a square. This function doesn't look anything like the sinusoid presented earlier, but we will see that with enough frequencies, any signal can be reconstructed perfectly. Right now we have only used 1 frequency, so everything looks the same. 2 frequencies and we can already see some differences. Here's with 3 frequencies. And 5. And 10. Now, the amplitudes have become too small to see, but they are there, and as we keep adding more frequencies, the result looks more and more like the original signal. Here's with 50. And finally, using all the frequencies, we get our original signal back. Here's how it looks like when you zoom in. Okay, so any signal can be decomposed into a sum of sinusoids. What if we wanted to use something other than sinusoids? For instance, could we decompose a signal into a sum of square waves, deltoids, or that weird Batman symbol? Surprisingly, the answer is yes, as long as the basis signal respects a certain property. The technique relies on inverting a matrix that is dependent on the basis signal we use. The details on how to obtain this matrix are in the GitLab project, but we will see that the butterfly signal doesn't work because its matrix is not invertible. That is, its determinant is 0. Let's visualize how a sinusoid decomposes into our 6 signals. The sinusoid will be written as a sum of basis signals with varying frequencies, amplitudes, and rotations similar to the regular Fourier transform. The only difference is that we won't be using sinusoids. So here's 1 frequency. Now with 2. 3. 5. And 10. We can see that all the signals except the butterfly resemble a sinusoid more and more. Continuing, here's 50 frequencies. And finally, using all the frequencies, we obtain a perfect sinusoid. With all frequencies added, it might look like the butterfly signal is indeed capable of decomposing a sinusoid, however this is nothing more than a numerical error, because the matrix's determinant is very close to 0, but not exactly 0. Here's how it looks like now when we zoom in. Okay, so we can use these 5 functions to decompose a sinusoid. What about decomposing any arbitrary complex signal? The answer is yes. In fact, the property mentioned earlier depends only on the choice of the basis signal, so the signals presented here, except the butterfly, can be used to decompose any complex signal we want. As a last demonstration, we will decompose this signal obtained by tracing the contour of an image. This is the same method by which the Batman and Mandelbrot waveforms were obtained, and you can find more details about this in the GitLab project. Since we've determined that the butterfly doesn't work, I'll be showing the sinusoid in its place. So here we go again with 1 frequency. 2. 3. 5. 10. And 50. We can see that this function is much more complicated, so more frequencies are required to reconstruct it. Finally, when we add up all the frequencies, we get the original signal back exactly. Here's how this one looks when we zoom in. So that's the main idea that I wanted to show, that not only sinusoids can be used to decompose arbitrary signals in the same manner as the Fourier transform. The link to the GitLab project is in the description. It contains some details about the math involved to do this, as well as a Jupyter notebook that you can use to generate the animation shown in this video. I have only seen animations with sinusoids before, so I hope you found this interesting. I leave you with one more animation which shows how the reconstructed signal changes as we add more and more frequencies.